Hello all, I am Dr. M. Shanti from Department of Physics, Kamaraj College of Engineering and Technology. In this video, we discuss about the heat conduction in compound media. The heat conduction in compound media comprises of two systems. One is bodies in series. Bodies in series. In bodies in series, two different materials having thermal conductivity of different values are arranged in seriously. We stack the materials in series position. And another one is bodies in parallel. So, two different materials are arranged in parallel. For simplicity, we have considered only two systems. We can extend up to n number of systems. So, in this derivation part, we consider two systems. First, we discuss about the heat conduction in bodies in series. So, here two different materials P and Q are considered. P is the material having thermal conductivity K1, Q is the another material having thermal conductivity K2. The thickness of the material, first material P is taken as D1 and the thickness of the material Q is considered as D2. Thermal conductivity is taken as K1 and the another material Q is having the thickness D2 and its thermal conductivity is taken as K2. So, two different materials having two different thermal conductivity values are sandwiched together in series condition. Let us consider the area of cross section of both the materials are A. The area of cross section of the material P and Q is A. The material P and its thickness is D1 and then the another material Q is joined with the material P, its thickness is D2. Then this compound medium is subjected to heat at one end. This compound medium is subjected to heat at one end. So, obviously, this end will be hot comparatively compared to this hot end, this phase will be cold. Let us take the temperature at the hot end is theta 1. The temperature at the hot end is theta 1 and the temperature at the cold end or the opposite phase is taken as theta 2. At the interface, we assumed that the temperature is theta. Now, we have to write the equation for the quantity of heat conducted by this compound media. The quantity of heat conducted by the material P is given by the quantity of heat conducted per second through the material P. The first material is given by Q is equal to K1A theta 1 minus theta by D1, where K1 is the thermal conductivity of the material P and the A is area of cross section. Theta 1 is the temperature of the hot end and for the material P, theta is the cold end. So, theta 1 minus theta divided by D1. Here the D1 is the thickness of the first material P. Then we have to write the quantity of heat conducted through the material Q. The quantity of heat conducted through the material Q is given by. So, here for the second material, the thermal conductivity is K2. The thermal conductivity of the second material is K2. Its area of cross section is A. At the interface, we have to consider the interface and the second material, hot end to the cold end. So, the hot end for the second material is theta and the cold end is theta 2. So, theta minus theta 2 by D2. Here the D2 is the thickness of the second material Q. After heating the compound media for a long time, the steady state is reached. So, the quantity of heat conducted through the material P is equal to the quantity of heat conducted through the material Q. So, we write the quantity of heat conducted by the material P expression is equal to the quantity of heat conducted through the material Q. So, we are equating these two equations which we have written previously. Here we want to find out the temperature at the interface of the compound media. At the joining point we have to find out the temperature, that is we want to find out the temperature at the interface, that is theta. We want to find out theta. So, we are rearranging the terms. So, on rearranging the terms we get, so first multiply individually with the K1 and the theta 1 on both sides, the A got cancelled. So, K1 theta 1 by D1 and then K1 theta by D1 which is equal to K2 theta by D2 minus K2 theta by D2. So, in order to get the theta value, the temperature at the interface, we are rearranging the terms. The theta values are arranged in one side of the equation, whereas the remaining terms are aligned in the other side. On rewriting the expression, we are aligning the theta value in the left hand side of the equation. We get the expression for theta as K1 theta 1 by D1 plus K2 theta 2 by D2, the whole divided by K1 by D1 plus K2 by D2. Now, we have determined the temperature at the interface of the compound media. Now, we have to substitute the temperature theta value in the quantity of heat conducted by the material P. So, already we know the equation for the quantity of heat conducted by the first material, that is P. It is given by Q is equal to K1A divided by D1. It is given by theta 1 minus theta. So, in the place of theta, I am substituting, already we have derived this expression in the previous. So, I am substituting the value of theta here. So, we get the equation. So, then we have to take the common denominator in order to simplify the equation. We have to take common denominator on both the numerator and the denominator. First, taking common denominator in numerator, that is D1 by D2 is commonly taken. Then in the numerator it becomes K1 D2 theta 1. Here we are multiplying D2 and here I am multiplying D1. So, in the numerator part it becomes K1 D2 theta 1 plus K2 D1 theta 2 by D1 minus D1 by D2. And also for the denominator case also we have to take the common denominator. So, D1 D2 is the common denominator and the numerator will become K1 D2, cross multiplying these. So, we get K1 D2 plus K2 D1 divided by D1 into D2. So, we have taken common denominator in both the numerator and the denominator. Have written. So, in this expression we have to cancel the common terms. Here K2, here K2 D1 here in this expression K1 D2 theta 1 and here minus K1 D2 theta 1 is there. So, these two terms got cancelled. So, the remaining terms are K1A by D1 K2 d1 theta 1 minus k2 d1 theta 2 by k1 by k1 d2 plus k2 d1. In both these terms k2 d1 is common. So, taking these two terms before the bracket, I am writing the expression as the term k2 d1 is written before the bracket. So, it is simplified as k1a k2 d1 theta 1 minus theta 2 by d1. Here also d1 d1 are the common terms. So, d1 in the numerator and the d1 in the denominator got cancelled. The quantity of heat conducted Q is equal to k1 k2 a theta 1 minus theta 2 divided by k1 d2 plus k2 d1. So, on further simplification, the k1 by k2 term has to be simplified from this expression. So, the denominator is divided by both the numerator and the denominator is divided by k1 and k2. So, I am dividing both the numerator and the denominator by k1 and k2. So, here I am writing k1 by k2, it is divided by k1 by k2. So, it got cancelled. Here 1 k1 by k2 becomes, here also 1 k1 by k2. So, k1 got cancelled, here k1 got cancelled. So, d2 by k2 remains plus here k2 and k2 got cancelled. So, d1 by k2 is the remaining in the denominator. So, on simplifying this we get Q is equal to A into theta 1 minus theta 2 divided by d2 by k2 plus d1 by k1. Here A is the area of cross section of the material, both the material P and Q. Theta 1 is the temperature at the hot end, that is the one surface, one starting point of the material, and theta 2 is the temperature at the cold end. D2, D1 are the thickness of the two materials. K1, K2 are the K1, K2 are the thermal conductivity of the material, the two materials P and Q. So, for the two systems we have derived the quantity of heat conducted. By knowing the temperature of the hot end and the cold end, we can easily determine the quantity of heat conducted. For n number of systems, this equation can be rewritten as summation of I is equal to 1 to n. This equation can be extended up to n number of system. So, A theta 1 minus theta 2 divided by di by ki. So, this is the expression for the quantity of heat conducted by the compound medium having n number of materials. N number of material stacked in series condition. The n number of materials are aligned in seriously, and then the quantity of heat conducted is given by this expression. Now, we move on to the part bodies in parallel. In this system, the two materials are stacked in parallel way. So, parallelly we are applying heat along the two surface. So, the material P and Q are aligned in a parallel way. So, heat is applied at one end. The first material is having the thermal conductivity K1 and the second material is having the thermal conductivity K2. The thickness of the first material is D1 and the thickness of the second material is D2. The thickness of the first material is D1 and the second material is D2. Here the heat is applied. The temperature at this phase is taken as theta 1, whereas the temperature at the opposite phase is taken as the theta 2. Both the materials are retained at the temperature theta 1 at the opposite phase. Here in the hot end, both the material are retained at the temperature theta 1. Now, we have to calculate the net quantity of heat conducted through the material, through the compound media. So, now the quantity of heat conducted by the material X is given by Q1 is equal to K1 A1 theta 1 minus theta 2 by D1. For the first material, the quantity of heat conducted is given by K1 A1 theta 1 minus theta 2 by D1. And for the second material, the quantity of heat conducted is taken as K2 A2 theta 1 minus theta 2 by D2. So, the quantity of heat conducted by both the materials are written. Here we have to note that the area of the cross section of the material X and Y are taken as different values. In the previous case, we have considered the area of cross section is same for both the materials. In this case, we are consider the area of cross section of the material X is different from the area of cross section of the material Y. So, I have taken the area of cross section of the material, first material X is A1 and the second material is A2. The net quantity of heat conducted through the two material X and Y is given by, the net quantity is given by Q and it is calculated by adding Q1 plus Q2. So, this is the net quantity of heat conducted by both the material X and Y. It is given by K1 A1 D1 K1 A1 by D1 plus K2 A2 by D2 into theta 1 minus theta 2. This is for the system stacked in, this is for the two systems stacked in parallel condition. This can be extended for n number of systems. So, instead of K1 K2, I am writing the summation value. Summation I is equal to 1 to n. The summation can vary from 1 to n number of systems. So, summation I is equal to 1 to n Ki Ai by Di. Commonly I am writing Ki Ai by Di into theta 1 minus theta 2. The quantity of heat conducted through the compound media which is stacked in parallel is given by summation of I is equal to 1 to n Ki Ai by Di into theta 1 minus theta 2. So, in this video we have calculated the heat conducted through the compound media which is in both are in series and parallel condition. In this video we have calculated the quantity of heat conducted through the compound media which is aligned in series and parallel condition. Thank you.